Now let's find the limit of a rational function as it approaches a positive infinity with an example specifically dealing with a slant asymptote as we're going to look at here. So we need to find the limit of this function as x approaches infinity. Again, keep in mind that one of the most effective methods in finding the limit of a rational function is taking everything and dividing it by the degree of the denominator. The degree of our denominator is just an x to the first. So what we're going to do is we're going to take the limit as x approaches infinity, and we're going to divide everything in this rational function by x. So that's just going to look like 2x squared over x plus 6x over x minus 2 over x. Same thing for your denominator, x over x plus 1 over x. Now, when we simplify this, well, this x cancels with one of these x's, leaving us with 2x. This x cancels with that x, making it a plus 6, right? Minus 2 over x over, let's see, x over x is a 1 plus 1 over x. At this point here, after we've simplified, go ahead and plug in a positive infinity. So I always just think about plugging in like 100 billion, right? So if I plug in a super large number to a fraction here, if I'm plugging into the denominator, that's going to make it go to 0. The larger the denominator, the smaller that is going to be. So that means this one is going to be 0. This one is going to be 0. That really just leaves us with a 2x plus 6 over a 1. So this is really what we're looking at here. So this is what it's going to break down to. We are going to find the limit of that function as it approaches a positive infinity, the limit of that function as it approaches a negative infinity. So if we take a look at this and think about plugging in a positive infinity, a super large number, if we plug in 100 billion into x, multiply it times 2 plus 6, it's just going to be even larger. So the larger and larger and larger number that we can think of and plug in here, this is just going to get bigger and bigger and bigger, which means the limit as x approaches a positive infinity is a positive infinity. If we plug in a negative number, right, a negative infinity, think negative 100 billion, negative 100 trillion, right? A negative times a positive is going to be negative, right? And that's going to be a super, super large negative number. So it doesn't matter if we add 6, it's still going to be really, really negative. So that means the limit as x approaches negative infinity is going to be a negative infinity. Now, this problem wants us to find the limit of this rational function as it approaches positive and negative infinity, but it actually also wants us to determine the end behavior of this of this function. So we're going to use our limits here to determine our end behavior. Now, if we take a look at this graph, so we know the further we go positive, it's going to shoot off to infinity. The further it goes negative, it's going to shoot off to negative infinity. But one thing about rational functions, if the degree of the numerator is just one more than the degree of the denominator, right? We have a degree of a 2 here, degree of a 1 here. If the numerator is just one more than the denominator, which this one is, that is a sign that we have a slant asymptote for this example here. In order to figure out what that slant asymptote is, we need to divide this out. We need to take our numerator, 2x squared, plus 6x minus 2. And we need to divide it by our denominator, x plus 1. So we actually need to do this division. X goes into 2x squared, 2x times. When we multiply that, we get 2x squared plus 2x that we'll need to subtract. If you need a refresher on long division, I do have a video on that. Just search it up on my channel. Otherwise, 2x squared minus 2x squared cancels. 6x minus 2x is a 4x, and drop down that minus 2. X goes into 4x 4 times. And if we multiply 4 times our divisor, we get 4x plus 4. When we subtract that away, 4x minus 4x goes away. Negative 2 minus 4 gives us negative 6. So our remainder is a negative 6. We don't need to focus on a remainder. This 2x plus 4 does represent our asymptote, our slant asymptote for our function. So that means if we go up 4 and then do a slope of a 2, right? Up 2 over 1 or down 2 over 1, down 2 over 1. We are going to have a slant asymptote that looks something like this. Now, based off of our limits To the right-hand side over here, it does say that it's going to shoot off to up infinity. On the left side, it's going to shoot down towards negative infinity. And actually, just to add just a tiny bit more information to our graph, if you are allowed to use a graphing calculator or use a website real quick to plug this in, I would do so. Based off of our denominator, x plus 1, if you set your denominator equal to 0 and solve, it will tell you your vertical asymptotes. So we have a vertical asymptote at a negative 1. Okay. So going back to our asymptotes, or our end behavior for this graph, on the right hand side, our graph is going to shoot up to the positive over here. So it looks like our graph on the right hand side, again, it wants to follow these asymptotes on the on down here. It's going to shoot down, but again, we're worried about our end behavior. So our end behavior on the right side is going to be positive to positive infinity, and it's going to follow these asymptotes, and it's just going to go higher and higher and higher to positive infinity. On the left side of our asymptotes, our graph is going to do this type of thing here, all right, where it's going to shoot down to a negative infinity, and it's going to keep going negative to negative infinity there. So our end behavior down on the left, up on the right for this function based off our slant asymptote, our vertical asymptote, and the limits that we got here.